In this lecture, we shall consider solving another cantilever beam problem for finding the shear force and bending moment values along the beam length. Let's have a cantilever beam AB with end A free and end B fixed. A right-angled extension frame at the free end A is provided as shown with an inclined point load of 20 kilonewtons acting at the top end with a slope or gradient of 4 units in vertical direction and 3 units in horizontal direction. The vertical part of the extension frame is labeled A and the horizontal extension part is labeled B, where A equals 0.2 meters and B equals 0.1 meter. Important key points of loads on the beam are marked and labeled as C and D. We now mark the given lengths of the parts of the beam. Additionally, we place a uniformly distributed load of ordinate 20 kN per meter between the part CD. Also, a uniformly varying load of ordinate 0 kN per meter at C and 30 kN per meter at D is placed on top of the uniformly distributed load, so that the total load at point D reads 50 kN per meter. We mark an arrow pointing towards the right from the free end A, indicating the reference end from which the distance of an imaginary section is measured. We now draw projections from the key points. The given beam is simplified and now schematically redrawn to show a vertical load of 16 kilonewtons and a horizontal load of 12 kilonewtons, together with a net moment of 12 kilonewton times 0.2 meters minus 16 kilonewton times 0.1 meter to get 0.8 kilonewton meter, all acting at the free end A. We complete the figure by showing the remaining loads acting on the part CD. The zero baselines for axial force, shear force and bending moment diagrams are drawn and labeled accordingly. Now, for the region AC for which the variable x is greater than and including 0 and less than and including 2 meters, the axial force at x is written as plus 12 kilonewtons, which is a constant value indicating tension within the part created. For region CD for which x ranges between and including values 2 and 4 meters, we first find the ordinate of the unknown uniformly varying load at a distance x meters from the reference. We denote it by the question mark symbol, and using the similar triangles theory, we write question mark over x minus 2 equals 50 minus 20 over 2, giving question mark as 15 times x minus 2 kilonewton meter. Now the axial force at x again equals a constant value of plus 12 kilonewtons, since there is no intermediate horizontal load present throughout the beam except the free end and the fixed end. Hence, for region DB, for which x varies between and including 4 and 5 meters, the axial force at x is again shown to be a constant value of plus 12 kilonewtons. The shear force at x for the region AC can be written as minus 16 kilonewtons, a constant value. For region CD, the shear force at x is written as minus 16 minus 20 times x minus 2 minus half times x minus 2 times question mark, that is half times x minus 2 times 15 times x minus 2 kilonewtons, which is found to be parabolic in terms of the variable x. The double derivative is found to be negative in sign, hence the locus is a maxima type of curve. For region DB, the shear force at x equals minus 16 minus 20 times 2 minus half times 30 times 2, which equals a constant value of minus 86 kilonewtons. The bending moment at x for the region AC is written as minus 0.8 minus 16 times x, which is linear. For region CD, bending moment at x equals minus 0.8 minus 16 times x minus 20 times x minus 2 times half of x minus 2 minus 7.5 times x minus 2 squared times a third of x minus 2. Note that we used 7.5 times x minus 2 squared as a replacement of the value of shear force for the uniformly varying load on the small part created by virtue of the section. This equation is found to be cubic in terms of variable x. The double derivative is found to be negative in sign, hence the locus of M at x for region CD is a type of maxima curve. Lastly, for region DB, M at x is written as minus 0.8 minus 16 times x minus 20 times 2 times x minus 3 minus half times 30 times 2 times the distance of this equivalent point load from the section, that is x minus 3.33 meters. This equation has a maximum power of x as 1. Hence, the locus of the moment values is found to vary linearly over the length. We now draw the ordinate values at various key points and the locus joining the ordinate values for various parts of the beam for the resistive axial forces, shear forces and bending moments in their respective diagrams. The maximum axial force is found to be 12 kilonewtons of tensile nature. The maximum shear force is found to be 86 kilonewtons and the maximum bending moment is found to be 210.8 kilonewton meter. As discussed earlier, these maximum values shall help us to find the respective induced stresses in the beam, which may be a possible cause of failure, hence aiding the designer to design the beam accordingly by varying the dimensions or using a better grade material or using some other mode of design. We hereby complete the discussion on cantilever beams. For further practice, 3 problems are provided in the form of schematic representation of the beams in the next lecture, along with the respective answer keys for reference.